We will now study a new type of convergence. This is called convergence in measure. So we will then study its properties and also its relationship to the other types of convergence which we have seen. Convergence pointwise, convergence almost everywhere pointwise again, and convergence almost uniformly. So all these interconnections we will see. Okay, so definition. Let X, S, mu be a measure space and Fn a sequence of real valued measurable functions defined on X. We say that Fn converges in measure to a function, to a real valued measurable function f if for every epsilon positive we have limit n tending to infinity of the measure of the set of all x in X such that mod fnx minus fx is greater than or equal to epsilon. This limit is equal to 0. So look at it carefully. So you take the set of all x such that mod fn minus f is bigger than or equal to epsilon. The measure of that set should go to 0 as n tends to infinity. So this is a different type of convergence. So we call this convergence in measure, and we write Fn converges to f in measure. So this symbol mu over the arrow, which will mean that it converges in measure. We say that a sequence Fn is Cauchy in measure if for every epsilon positive and for every delta positive there exists a capital N in N such that for all mn greater or equal to capital N, the measure of the set of all x in X such that mod fnx minus fmx greater or equal to epsilon can be made less than delta. That means the measure of fn minus fm greater or equal to epsilon can be made as small as you like for nm sufficiently large. So that is the corresponding idea of the Cauchy. So we would like to know what are the various properties of this convergence, what is its relationship to convergence pointwise, etc. And then of course the usual question, convergence, does it imply Cauchy in measure? Cauchy in measure, does it imply convergence in measure? And so on and so forth. Okay, so let us start with the following proposition. XS mu finite measure space. That means mu x is less than plus infinity. Fn real valued measurable functions defined on X converging almost everywhere to F. Then of course real valued and measurable. Then Fn converges to F in measure. So if you are in a finite measure space, then convergence almost everywhere implies convergence in measure. So proof, let D equal set of all x in X such that fn x does not converge to f of x, the set where the sequence diverges. Okay, then we are given that mu d equal to 0. So let epsilon be greater or equal to 0, and we set em epsilon equals set of all x in X such that mod fm minus is greater or equal to epsilon. So to show mu of em epsilon tends to 0 as m tends to infinity. Now what is the set where it does not converge? Does not converge means there exists an epsilon positive such that for every n you have, there exists an m bigger than n such that mod fmx minus fx is bigger or equal to epsilon. This is the definition of not converging to f of x. fnx does not converge to f of x means for every, there exists an epsilon such that for every n we can find an m which is bigger than n such that fm minus f is bigger or equal to epsilon. So this is the thing. So now this is nothing but union epsilon greater than 0 of the limb sup of n tending to infinity of en epsilon. So this quantity here is the definition of the limb sup. Okay, so we have already seen this. So now you have that since measure of D equal to 0, and these are all subsets of that, and therefore this implies that measure of limb sup n tending to infinity en epsilon equal to 0. Now mu x is finite, therefore everything is a finite measure in this set, and therefore we have given this, either done it or we have done it in the exercises. This is equal to mu of limb sup n tending to infinity en epsilon, which is greater or equal to limb sup en epsilon mu of en epsilon n tending to infinity. And this is true because mu x is less than infinity. So you have to use the continuity from above to prove these results here. Okay, and now you know that 0 is always less than or equal to lim inf n tending to infinity mu of en epsilon. Now that is less than or equal to limb sup. And we are saying limb sup is less than or equal to 0. Therefore you have a sandwich, 0 everywhere. So this implies that limit n tending to infinity mu of en epsilon equal to 0, that is fn converges to f in measure. Example, not true if mu x is infinite. So again you take capital X equal to n and s is equal to the power set of n and mu equals counting measure. So Measure of any set E less than epsilon, if epsilon is less than 1 or sufficiently small, this implies that E is empty. So this implies convergence in measure. When you want to say that this measure goes to 0, this should become empty after some time, and that means everything, for every x, for all n, it should be less than or equal to less than epsilon. That means Fn converges to F in measure is the same as saying Fn converges to F uniformly. So again, as earlier, consider Fn equals chi of 1, 2 up to n, then Fn converges to F identically equal to 1 pointwise but not uniformly. So you have pointwise convergence, but that does not imply uniform convergence in infinite measure spaces. Okay. Now, what about convergence in measure? So convergence in measure, does it imply convergence pointwise? Almost everywhere. So again the answer is no. So we have the following example. Take x equal to 0, 1 equipped with the Lebesgue measure, and then you define chi ni to be the characteristic function of I minus 1 by n, I by n, okay, 1 less than or equal to I less than or equal to n. So you are taking n and then 0 to 1 and dividing it into n equal parts, and therefore you will have n subintervals each of this length. Okay. So now you look at the sequence chi 1 1, then chi 2 1, chi 2 2, then chi 3 1, chi 3 2, chi 3 3, and so on. Now for each n in n, there exists exactly one I, 1 less than or equal to I less than or equal to n, such that, so let x belong to 0 1, chi n I of x equal to 1 and chi n j of x equal to 0 for all j not equal to I. So that means if you look at this equation, you will have a 1 for the first one, then one of these will be 1, the other will be 0, then one of these three will be 1 and the rest will be 0, and so on. So there will be a 1 which is popping up all the time. So this implies chi ni x does not converge for any x. Okay, so this therefore this is you don't have pointwise convergence. But what about convergence in measures? So if you take epsilon less than 1, then measure of set of all x in 0 1 such that chi ni x is greater than or equal to epsilon. This is precisely measure of I minus 1 by n, I by n, because there alone it is 1, everywhere else it is 0, and that's equal to 1 by n, and that goes to 0 as n tends to infinity. Therefore, the sequence converges to 0 in measure. So it converges in measure, but it does not converge pointwise. But if you look at this carefully, you can look at this sequence once again, and then there exists a subsequence which you can pick out, namely just take one from each n, the I where it is 1, or if you take the one from where it is 0 for each n, then also you will get a subsequence which converges. So you have a subsequence which will converge pointwise. Okay. So proposition XS mu measure space Fn sequence of measurable real valued functions converging in measure to f real valued measurable. Then Fn has a subsequence which converges to f almost everywhere. So proof, we can do this in several ways, and I am going to use now, we will indicate a proof, under proof later on. So we are going to use the Borel-Cantelli lemma. So remember the Borel-Cantelli lemma. So if you have Fi in S, sigma mu of Fi is finite, then there exists an f mu f equal to 0, and for all x in f complement, x belongs to at most finitely many Fi. Okay, this is the Borel-Cantelli lemma. So we are going to use this. We have proved this in earlier, and this is a very nice application of that set of that lemma. There are several nice applications of Borel-Cantelli, especially in probability theory, which is you can say so therefore in measure theory also, and therefore this is one such. Okay, so we are going to define ENM is set of all x in x such that mod fnx minus fx is greater or equal to 1 by n. Then for every m, we know, so Fn converges in measure to mu, implies mu of E and m tends to 0 as n tends to infinity, implies there exists a n0 of m such that mu of E n0 m can be made as small as I like, and I am going to say 1 by 2 power m. Okay, m is fixed, so I am going to choose in this fashion. So now if you take sigma m equals 1 to infinity, mu of E n naught m, this is equal to, this is finite, this is a convergent geometric series 1 by 2 power m, and therefore it is finite. So by the Borel-Cantelli, there exists a E such that mu E is 0, and on E complement x in E complement implies x belongs to at most finitely many E n naught m. Implies there exists a capital N such that for all m greater or equal to n, x does not belong to E n naught m. That is, mod Fn naught m x minus f of x is less than 1 by m for all n m greater or equal to. This means that Fn naught m converges to f for every x in E complement. That is, Fn naught m converges to f almost everywhere. Okay, so this completes the proof. So very nice application of, so given any sequence converging in measure, you can always find a subsequence which converges pointwise almost everywhere. Okay, so finally, before closing this section, we will of course return to this. We'll study much more, but for the moment, the last result I want to prove in this session is that the limit, you see, whenever you have a sequence which converges in some sense, you want the limit to be unique. Okay, so this is what we are going to say here now. So excess mu measure space. So Fn sequence of real valued measurable functions. Fg real valued measurable functions such that Fn converges to f in measure and Fn converges to g in measure. So suppose there are two such, can you have two such limits? Then f equal to g almost everywhere, which is as good as unique, because what do you mean by convergence in measure? It means that the limit of the set where it disagrees, which does not converge to, has to be 0. So, but except on the set of measure 0, these two are equal, and therefore this is as good as saying that the limit is unique. So you have uniqueness up to equality almost everywhere. Proof. So let epsilon be positive. So you then take set of all x, so set mod fx minus gx greater or equal to epsilon. So this is contained in set of all x, so set mod fx minus gx is greater or equal to epsilon by 2 union set of all x such that fnx and fnx minus gx greater or equal minus fx and minus gx greater or equal to epsilon by 2, because you have mod f minus g is less than or equal to mod fn minus f plus mod fn minus g. So if both of these are less than epsilon by 2, then f minus g will be less than epsilon by epsilon, and therefore if you have f minus g greater or equal to epsilon, at least one of these two must be true, and therefore you have that this is contained in this. But Fn converges in measure to f, Fn converges to measure in G, and therefore this goes to 0 and this also goes to 0 as n tends to infinity. And this implies that set of all x such that mod fx minus gx greater or equal to epsilon is 0 for every epsilon positive. So set of all x, so measure of this. Okay. Now set of all x is that mod fx minus gx greater than 0 is nothing but the union over n equals 1 to infinity of set of all x in x such that mod fx minus gx is greater or equal to 1 by n for some n. It has to be, because if it's strictly positive, it must be greater or equal to 1 by n for some n. And then each of this is of measure 0, and therefore this implies that mu of set of all x in x such that mod fx minus gx greater than 0 equal to 0, that is f equals g almost everywhere. Okay, so that proves this. So we will continue with convergence in measure next time.